this lecture, I will show you how Semilog paper is made, and I will show you how to use it. This is for Chapter 4 for Math 107. You might have noticed that graphs of exponential equations are hard to draw, and they're also difficult to read with any kind of accuracy. For example, here's a plot for bacterial growth starting with 300 and a half-life of 20. Not unreasonable. And you can see if you plot it out, this would be 10 half-lives. If 20 is 20 minutes, that's only 200 minutes, which isn't, unreasonable. You'll see that the graph gets almost vertical here, so that although you could isolate various values in y and the amount here, it'd be very hard to figure out exactly where you were time-wise. And if you're down here closer to the origin, you see how the graph is almost horizontal here, and you can't really resolve any y values. So it is hard to read, and of course it's not a straight line, which makes it harder to draw. Now watch what happens when you take the log of both sides of the equation. I'm just using the general equation here for growth, which would be a equals a naught, starting amount, times 2 to the t over the doubling time. If I take the log of both sides, the right-hand side breaks up into two pieces, remember. I'll write it again here. Log of a times b equals the log of a plus the log of b. So that's what has happened here. So this is broken out, the log of a naught, and then since this is multiplied, then here's the log of 2 raised to the t over d power. Of course, you're taking a log there, that t over d comes out. Let me write the intermediate step for that. So I have the log of 2 to the time over the doubling time. Because it's a log, the t over d comes out in front, and I have the log of 2. So that explains this step right here. Now we can rearrange it a little bit. I could put the term with the variable t out in front, and then I have log 2, which is just 0.3010, just a number, divided by the doubling time, plus the log of a naught, which again is just a number. That's because a naught is your initial value. This is a linear equation in t, in time. It's linear. I've taken the log of both sides and I got a linear equation. Here's an example. Say the initial amount was 300, so that meant a0 was 300. And the doubling time is 20, so d is 20. So substituting those values into this equation, we get log a equals 0.15 t plus 2.48. Forgetting for a moment what this log of a is, just call it y. You can see that is a linear equation. It has a slope here of 0.15 and a y-intercept of 2.48. And as expected, here's the graph. Alright, log a. So this is the log of the answer I wanted. Here is time, or whatever t is. Right. And now you see, because I've taken the logarithm, I now have a straight line. Straight lines are easy to draw. They're also very easy to read. There's one problem though. Over here, I have the log of a, but I want, I want or need a itself, not the log of a. So although I can draw this nice graph, once I get done with it, I have to go back. I have to say I'm at this point here, 60, and I find this point on the graph. I can go over here and read what this is if I had a decent scale. Then I would have to take this number, I'd have to punch that into my calculator and find a. Remember that the log, the inverse of log is exponentiation. So okay, you could do that in your calculator. But it's not handy. So here's a little bit different approach. Let's look at taking the inverse of the log of a just by writing a list of common values. I know if a was 2, then the log of a would be 0.3010. I could go down this whole list. Log of 10, if a was 10, oh, I don't have the pen, sorry. So the numbers here are really the values of a, and this is the log of a. And so if a was 10, the log of a would be 1. And now, because I would have to be doing this over and over, the idea is to draw these values onto the graph paper. So if you remember, the log of 2 was 0.3010. Okay, that means this is a graph of the log of A. All right, so when you encounter the value of 3010, you know that A itself, this is a log of A, then A itself must be 2. It's like, instead of going and calculating everything on my calculator, I'm just going to put some special values on here. I know if I ended up at 0.4771, such as the point right here, then A would be 3. I could keep going all the way up here. The top one, I'm sorry, A would be 10. Right. Notice the spacing. There's a big gap here to get to the 2, the 3, and then as you go up, they kind of scrunch together till you get to 1. All right. So every one of these gives me a value of A for some special value. Nice even values, and then this top one, 9, and then 10. Okay, here's the brilliant idea behind Semilog paper. The idea was, well, because I would have to go over here, find this value, put it in the calculator, and find this, why not just use this as the scale and dispense with this part over here? My pen doesn't want to go there. I guess it doesn't want to get rid of those values. Okay, so I'm going to use this as my scale. I don't need these intermediate results, because once I get them, I'm going to get rid of them. Now notice how these lines are kind of scrunched up. There's a big jump, like I pointed out before. By doing what I said, getting rid of the log scale and just using the answer, so to speak, you get semi-log paper. It's semi-log because only one axis is logarithmic. And you can tell this is logarithmic by the spacing. There's a big jump to 2, then 3, 4, 5, 6, 7, all the way up to 10. So if you didn't totally understand that first part, you can surely ask me about it, but you still will be able to use and read semi-log paper even without understanding it. The basic steps are that your exponential equations are hard to read and hard to draw. But if you take the logarithm of both sides, you end up with a straight line, which is very nice to work with. The problem is that you end up with the log of A instead of A itself. Then you have to go through a calculation. Well, someone, and I don't know who it was, got this brilliant idea to just use the integer results for the scale and forget the logs. The only thing is that you're going to get this nonlinear scale. You can go between more than 1 and 10. I'll show you on the next slide. You can tell it's a semi-log paper here by the spacing. Okay, and you see the spacing repeats, and I'll show you how that happens in a minute. But each one of these is called a cycle. So here's a cycle from 1 to 10. Here's another cycle. Here's another cycle. And then it goes on like that. So each cycle has the same spacing. Now look at the counting. We've got 1 here, 1, 2, and then 3, 4, and 5. 3 and 4 aren't marked, and then 5, 6, 7, 8, 9, 10. Now when I start with 10, then I count by tens. 10, 20, 30, 40, 50, 60, 70, 80, 90, and get to 100. Now with 100, I start counting by 100s. The next line after this would be 2,000. Right? Here's why that works. Let's start with the log of 20. The log of 20 is 10. That's really the log of 10 times 2. So I can break that out as the log of 10 plus the log of 2. But the log of 10 is 1. And then I just have the log of 2, so I just have 1.3010. And you see, if you look at the decimal part here, that is just the scaling that we saw originally, that sort of scrunched up scaling that we saw. Here's the big jump, not so big a jump, and then closer and closer together. If we take the log of 200, we'll start seeing the pattern again. This would be the log of 100 plus 2. Well, log of 100 is 2, so this becomes 2.3010. I take the log of 300. That's the same as a log of 100. Ooh, that's a log written there, sorry. Plus the log of 3, so it's 2.4771. And you see the decimal part continues again, but now we have 2. And if we go to the thousands, we'll have 3 out here instead of the 2 or the 1 that we had before. And here's that Semilog paper again, and this includes 3 cycles. Often when you get the Semilog paper, it doesn't have any cycles written on it. It doesn't have the 1, the 10, the 100, but it just shows, you order it by how many cycles you want it to show, 3 cycles, 5 cycles, and then you write in your own numbers. And each one will be a power of 10, so this is first power of 10, second power of 10, third power of 10. And you can see the counting there. So here are the benefits of the Semilog paper. The paper takes the log and straightens out the graph. And then the paper also takes the inverse of the log along the y-axis and gives you the answer. So this is very good, and it addresses the 2 problems with exponential equations and the graphs of exponential equations, that they're hard to draw. Well, the straight line is not hard to draw and hard to read, and then you eliminate that as well. Also, you can show very large and very small numbers on the same graph because each cycle is the power of 10. Like I said earlier, you can use and read Semilog paper without totally understanding what I just said about how it's made or how it was derived. And the way to use it is you just solve your equation and then you fill in the numbers, but you use the scale on the right hand side for where you're going to put your dots, and then you just connect them up, and you will see that you will get a straight line if your equation was exponential. You will get a curved over line if your equation was initially linear. So here's the typical equation for bacterial growth. You should know that pretty well now. A naught times 2 to the t over the doubling time. Let's say the doubling time is 40 minutes and you start with 100. A0 is 100. So this is your equation. The time constant is 40, so we'll count by 40 and get some data points. And here's the actual time. Whoa, I thought that was a marker. So here's the actual time in minutes. So I'm counting up. I do 10 time constants and I count up to 40 minutes. And here are the values. Because I count by time constants, remember, I'm going to be doubling every time I move one time constant. From 3 to 4, I double. In this case, 800 to 1600. So if I plot this on regular paper, regular linear paper, then I will get this hard to read exponential graph. And you can see this is linear because the spacing here, well, even if you don't have a grid, you can see that the numbers are spaced equally. 25,000 between each number. So that's linear spacing on both axes, so this is linear paper. The scale up here is time constants, and here is time in actual minutes. Here is the same equation but graphed on Semilog paper. The scale over here on this side is logarithmic. Well, that isn't helpful at all. The vertical scale is logarithmic. But the horizontal scale is still linear. That's why it's called Semilog paper. Otherwise it would be called log paper. And they have that too. Okay, I know this is logarithmic because I can see the nonlinear spacing between the numbers. Here's 100 to 200, and this would be 300 right in here. 400, 500, and you can see how the spacing is. It's that logarithmic spacing. This is the first cycle. Here's the second cycle. This paper had 3 cycles on it. Now, how do you plot the numbers? Well, all you have to do is put the data points onto the graph and connect them up. So at time 0, we had 100. This was our first data point. When we moved one time constant, that doubled to 200. Well, that would be one time constant, or 40 minutes. later, I'm at 200. When I went 3 time constants, no, 2 time constants, 80 minutes later, then the 200 doubled to 400. Well, this is 200, this is 300, this is 400, and that's why I put the dot there. Go another time constant, that doubled to 800. You see 800 is really scrunched up there, but that's where you put the dot, and you keep going like that. Okay, so all you do is put the dots of your data. You don't have to take any logarithms at all. All you do is put the dots of your data, but you have to fit it into this funny looking scale on the side. And when you do that, you will end up with a straight line once you connect the dots. The paper is also used for radioactive decay. Here's the standard equation. Let's say you start with 100 and have a half-life of 100. So the time constant is 100, and we'll count by 100s to get the pattern. So here are the values. I'm moving by time constants. That means I'm counting by 100. And every time I move by one time constant, the amount decreases by a half. This is decay. Go from here to here, it decreases by a half. If I plot it on linear paper, then I have the typical exponential decay. Here's what it looks like on Semilog paper. Notice the scale here. This is going from 10 to 100, so here's one cycle. But what was the cycle right before 100? It was 1 to 10, and now we're dealing in powers of 10, so now we have 10 to the minus 1 for the next scale. Same spacing. Okay, and again, you just take your points and put them on the graph. You started with 100. In one time constant, you had 50. This would have been a data point. In 2 time constants, you had 25. And actually, the spacing is non-linear in between these, but you don't have to worry about that. Just get it close. In 3 time constants, you have 6.25. No, where was I? 12 and a half. I'm sorry. Here's the 6.25 at 4 time constants. So all you do is put your data points in. So that's your Semilog paper. Very handy for anything that's exponential.